First thing, just to recap what we talked about last time, is that if we are dealing with a parametric curve or a vector valued function, I like thinking about them like parametric curves. Another way of thinking about a parametric curve is like the path of an object moving through space. And if we think of a parametric curve like the path of an object moving through space, then we can think of t as time. And so this, this equation where my x coordinate is a function of t, my y coordinate is a function of t, and my z coordinate is a function of t. This equation is sort of telling me the position of the object in space at any given time. So it's telling me all the information I need to know about the path and how the object traveled along the path over time. And if we take this mindset, then the velocity of this object at any given time is going to be a vector. And that vector is just the derivative with respect to time of each component individually, right? And then the acceleration vector would just be the derivative of the velocity with respect to time, so that would just be the second derivative of the position with respect to time. That was the brief summary of what we talked about yesterday. Huh? I haven't decided on the homework problems yet. Yeah, sorry, I was in a rush this morning, so I haven't actually picked out homework problems. But I'll try to by the end of class. I'll assign some homework problems. So, again, if I have a parametric curve and I call it P of t, and this is defined by x of t, y of t, z of t. Talked about what that means. The derivative of a parametric curve is also known as the tangent vector to that parametric curve. And I just said this not 10 seconds ago, but this is also the same thing as like the velocity of the object that's traveling along the parametric curve as a function of time. And this should kind of make sense, because if I have this parametric curve P, and I think at some given time my object is right here, and I take the derivative, then this tangent vector is going to be describing my velocity, right? And your velocity should be in the direction that's tangent to the path your object is taking at any given time. So that's what it means to have a tangent vector. One thing we're going to talk about today is the unit tangent vector. So the unit tangent vector, we're going to call that capital T. So lowercase t is time. Capital T is referring to the unit tangent vector. And so the unit tangent vector is just going to be the tangent vector, which would be the derivative, divided by the norm of the derivative, right? So whenever you divide by the norm, that just makes sure the magnitude of the vector is 1. And if the magnitude of the vector is 1, that's what we call a unit vector. So the unit tangent vector is just a tangent vector with magnitude 1, and this is the formula. So this sort of gives the direction of the velocity. but it doesn't give you the speed, right? We're sort of dividing by the speed so that, it's telling you the direction your object is moving, but it's not telling you how fast the object is going whenever you give a unit tangent vector. So that's going to be one thing that shows up in your homework problems and on your tests, is we'll ask for a unit tangent vector. You just have to know that that's a unit vector tangent to the parametric curve, so you just take the derivative and divide by the norm. Okay. The next vocabulary word over here is the normal vector. So a normal vector, whenever we are talking about a surface, the normal vector was just a vector that was orthogonal to the surface. When we were talking about planes in 3D space, the normal vector was just orthogonal to the plane. If we're talking about a normal vector to a parametric curve like this, the normal vector is any vector orthogonal to a tangent vector. And there's actually infinitely many normal vectors. Right? So we're talking about 3D space. So this is going to be harder for me to draw. Instead, I'll just use this, right? Or this. So if this pen, it's magnetic. If this pen is my tangent vector, right? It's tangent to some curve in space, so it's over here in space somewhere. This is my tangent vector minding its own business. This would be a normal vector because it's orthogonal, but leaving my tangent vector alone, I can actually define infinitely many normal vectors because there's infinitely many vectors that would still be orthogonal to the tangent vector, right? You just have to sort of rotate there's a whole plane that's orthogonal to my tangent vector, so the normal vector is any vector that lives in that plane. Does that make sense? Okay, so there's infinitely many normal vectors because a normal vector is just any one of those vectors that's orthogonal to the tangent vector. So this definition shouldn't surprise you, but a unit normal vector is just a normal vector with magnitude 1. Just like the unit tangent vector was just a tangent vector, but with magnitude 1. Okay. So then if we talk about the second derivative of a parametric curve, we also thought about the second derivative of a parametric curve as being sort of like the acceleration vector. If you're thinking about the path of an object through space over time, then the second derivative with respect to time would be the acceleration vector. So when we talk about the principal unit normal vector, we're going to represent with a capital N. And the formula here is capital T prime of t divided by the norm of capital T prime of t. So dividing by the norm is just what makes it a unit normal vector. And I've already told you that there's like infinitely many normal vectors that you can describe. This is one specific normal vector out of the rest that you get by taking the derivative of your unit tangent vector and dividing by its norm. And so it's kind of surprising, at least to me. I was a little bit surprised at first to think if you have the unit tangent vector and you just take its derivative, that's always going to be a vector orthogonal to the unit tangent vector. It's kind of neat. And since there's infinitely many normal vectors we can define, there's infinitely many vectors that are orthogonal to the tangent vector, what's special about this principal unit normal vector, sort of how we choose the specific direction, is this vector is always going to have the direction of course, number one, orthogonal to the tangent. Orthogonal to the tangent vector. And number two, in the same plane as t and the second derivative. So that second part, whenever I say it's in the same plane as the tangent vector and the second derivative, that sort of is going to nail down exactly which direction this normal vector is, right? There's infinitely many normal directions and infinitely many normal vectors in all sorts of different directions. But part two, when I say that this has to lie in the same plane as the tangent and the second derivative, that's what is going to specifically tell me what direction the unit normal vector is. So I'm going to try to draw a picture. We'll see how it goes. So here's some curve P. And here is some tangent vector, capital T. Let's say that the second derivative of P looks like this. It's like P double prime. Then the specific principal unit normal vector has to be orthogonal to T, but in the same plane as both T and P double prime. So maybe it looks something like this. I know it's hard to visualize because I'm obviously drawing on a two-dimensional piece of paper and we're talking about things that are happening in 3 dimensions, so it's definitely not easy to visualize or imagine. Let me give you another example. Let's say our path P was a circle. And a tangent vector would just be a tangent to that circular path. Then the principal normal vector would be pointing towards the center of the circle. I say that because if this particle were traveling in a circular path, if you've got an object that's traveling over time in a circular path, the velocity at any point is going to be tangent to that circular path, but the acceleration would be toward the center of the circle. I wish I had my little ball on a rope that I had last semester. But remember last semester I had a little tennis ball on a rope and I was swinging it around. The best way to be convinced, the best way I can convince you that the acceleration points towards the center of the circle is that whenever you're swinging a ball on a rope, the ball's traveling in a circle. I know the acceleration is towards the center of the circle because the only force that I'm applying to the ball has to go through the rope. So obviously the rope points from the ball to the center of the circle. That's the direction of the tension. That's the direction of the force. So that's the direction of the acceleration on the ball. Okay, so that's the case for like a circular path in 2 dimensions. If I wanted to try to like extend this to 3 dimensions, one of the paths that we've talked about so far was like a helix. So the curve might be something like cosine t, sine t, t. That would give this helix. So over time, in sort of like the xy plane, this object would be traveling in a circular path, but also over time in the z direction, this object is just traveling upward in the z direction at a constant velocity. If you take the derivative here, the derivative would be 1. So as a constant upward velocity. If I take any point like this one, and I take the tangent, of course the tangent's going to be x and y components tangent to the circle. The z component of this tangent is going to be slightly positive. Right? It's going to be a slightly positive tangent because it's also going up. As far as the principal unit normal vector, the principal unit normal vector is going to point directly towards the center of the helix, because all of the acceleration is pointed towards the center of the helix. And there's actually not any sort of vertical component to the principal unit normal vector in this case, because you're not accelerating upward at all. It's just constant velocity in the z direction. So that principal unit normal is just pointing horizontally towards the center of the helix. In fact, let's actually do the math then. So here is my equation for that helix over here. What if I ask you to find the unit normal vector? So I know that the velocity, or the first derivative, is going to give me a normal vector, or sorry, not a normal vector, a tangent vector. And so what's derivative of cosine? Yeah, negative sine. The derivative of sine is cosine. The derivative of t is 1. So this is a tangent vector. Of course, I could rewrite it like a column vector like this. Or I could rewrite it like, negative I sine t plus j cosine t plus k, 1k. Either way. All valid ways of writing a vector. So it's a tangent vector, but it's not a unit tangent vector yet. In order to get the unit tangent vector, which we call capital T, I have to take this vector and then divide by its norm. Good morning. So the norm is going to be the square root of each of the components squared and then added up. So you have like negative sine all squared plus cosine squared plus 1 squared. After like, here's your creative exam, and then here's your PTK project. All right. By the way, I've got PTK projects for Abdullah, George, and Gabriel. So Stephanie, Leah, Stephen, do you guys want to do honors projects or no? No. Okay. Okay. Just checking. Just double checking. All right. That's fine. Okay, so again, the norm of that vector, the one in green here, is going to be sine squared plus cosine squared plus 1 squared. So that is going to be this divided by the square root of what? 2. Yeah. So there's that Pythagorean identity for sine squared plus cosine squared, and so that's just square root of 2. So that means capital T of t is this vector. Negative sine of t over square root 2, cosine t over square root 2, and then 1 over square root 2. Or if you wanted to rationalize the denominator and be proper, this is how you write it properly. Or if you wanted to use IJK notation, then you could write negative root 2 over 2 sine ti plus root 2 over 2 cosine tj plus root 2 over 2k. All right. And so that is my unit tangent vector. Now, if I want to get the unit normal, the principal unit normal, I should say, the principal unit normal vector, capital N, that's going to be capital T prime of t over the norm of capital T prime of t. So t prime of t is just if I take the derivative of everything. Now the derivative of sine is cosine, so this is going to be first component minus cosine of t minus root 2 over 2 cosine t. And then the second component is going to be derivative of cosine is negative sine, so that's going to be negative root 2 over 2 sine t. And then the last component is a constant, so when I take the derivative, that goes to 0. So that is t prime of t. The norm of t prime of t is going to be the square root of, and I have to square each component and then add them together. So that's going to be root 2 squared is 2, 2 squared is 4, so that's going to be 2 over 4. That's going to be 1/2 cosine squared t plus 1/2 sine squared t plus 0 squared. So I will have t prime of t divided by the square root of what? 1/2. Yeah, because cosine squared plus sine squared is again 1, and so we're talking about 1/2. So I can take the reciprocal here and just call it root 2 t prime of t. So if I multiply every element of t prime t times root 2, what I end up with is negative cosine t, negative sine t, 0. That is my principal unit normal vector. And so this is a vector, like I said, is orthogonal to the tangent vector. It's in the same plane that is defined by the tangent vector and the acceleration vector, and it has magnitude 1. So it's sort of just telling you the direction of the curvature of a curve. is the best way to say it. And in this case, it should be pointing towards the center of the helix. Any questions so far? All right. So this is the last new thing we're going to learn today. If we have time, we'll do an example. Here's my path P. And so here's my object moving along this path, and it's moving along with some velocity, which is just given by the first derivative of P. But we'll call that the unit tangent vector. This principal unit normal vector is going to be sort of in the direction of the curvature. So this capital N is never going to point away from the curve, right? Like, so this is not a capital N, obviously, just because it's pointing away from how the thing is curved, right? So like if this is my curve, right here at this green point, would my principal unit normal vector be pointing up or down at this green point? It should be pointing down. It's in the direction that the curve is curving. And so if I put a green point right here, what about for this new green point? Which direction should it should be pointing up, yeah. If this is the principal unit normal vector, then it's pointing in the direction that your curve is curving. Okay. So the acceleration is going to look something like this. And we can talk about the tangential component of acceleration. And I can ask you, what is the tangential component of acceleration, as like a question on an exam. And I can also ask you about the normal component of acceleration. So these are two different scalar quantities. And the way it works is this. If this is my acceleration vector, and this is my unit tangent vector, and this is my principal unit normal vector. So these should be at a 90-degree angle if I draw them correctly, like this. Then what I'm about to draw in green, this would be the tangential component of acceleration, right? So like if I take the acceleration and I project it down onto the unit tangent vector, or the velocity vector, yeah, then that's what I get. So we're going to use this notation for the tangential component of acceleration. I'm going to use a lowercase a with a subscript capital T. So the lowercase a is for acceleration, the capital T is telling me this is the tangential component. So a subscript T is going to be the projection of my acceleration vector onto my tangent vector. So, you guys remember the formula for a projection? There should be a dot t over t dot t, which is a scalar, times the vector t. So t is giving you the direction, and that's how you find the tangential component of acceleration. Now, that capital T is a unit tangent vector. So if we actually found the unit tangent vector, then the magnitude of t is 1. And so that means what? T dot t is...
T squared.
Yeah.
Oh, it's 1.
Yeah, so it should be 1, yeah.
Yeah.
So t dot t should be 1, and so I actually don't need the denominator. That's just dividing by 1, right? So this projection would be a dot t, and this is actually, well, hold on. Let me rewrite some things. I should say that this projection of my acceleration vector onto t, that is a dot t times t. If I just ask you this, what is lowercase a with the subscript t, then this is just the a dot t part. Okay? So I'm making the difference because this is a vector and this is a scalar. Right? So remember, the dot product is when you multiply two vectors and you get a scalar as the dot product. So if I have a dot t, that's just a scalar that tells me the magnitude of the tangential component of acceleration. But if you want to know the projection of the acceleration vector onto the unit tangent vector, then that's the formula for the vector component. So that means this, since a is the sum of the projection of a onto t plus the projection of a onto n, this would be the projection of a onto n, then if I want to find the projection of a onto n, I could either do a dot n times n, and so a sub capital N would just be a dot n. Or alternatively, I could do this. I could say a minus the projection of a onto t is the projection of a onto n. And you could take the magnitude of the projection of a onto n, and that would work as well. So there's two different sort of pathways you can get to the same answer. So if we're talking about the tangential component of acceleration, this is like if you're driving and you step on the gas pedal. Right? So let's say our object moving through space is your car moving through space. If you really step on the gas pedal, like the acceleration that you're feeling is just making you move faster. It's increasing your velocity in the direction you were already traveling. Okay? So that's one type of acceleration, is if you were just increasing your velocity in the direction you were already traveling. That's like stepping on the gas, and then your car throws you back into your seat and you start going faster. That is what is meant by the tangential component of acceleration. Now, what if you don't change your foot on the gas pedal, you leave your foot exactly where it is, and so you're just maintaining your speed. Speed stays the same, but then suddenly you turn your steering wheel. Then if you turn your steering wheel to the right, then you sort of get thrown to the left, you know? Your car is actually accelerating even though your speed is staying the same. But the type of acceleration you're experiencing when you turn your steering wheel is the normal component of acceleration. So this is like keeping your speed constant and turning the steering wheel. You still experience acceleration. Acceleration just means a change in your velocity, right? And so the acceleration that you're experiencing is actually changing the direction of the velocity, right? Your car is maintaining the same speed or the same magnitude of the velocity, but what changes is the direction of your velocity is moving. So that's another way to think about acceleration. So this is what I remember, and this is kind of how I remember those two ideas. Okay, let's see if we can do an example in the next 8 minutes here. So, I've got this. It's this parametric curve, this path given by that. Okay, it's my x, y, and z components as a function of t. So if I eventually, my goal here in the end is to define what is a sub t and a sub n, the first step is going to be calculating the derivative. So we do the derivative here. I've got to use product rule. So it's et sine t plus et cosine t. And then for my y component, it's et cosine t plus et sine t, and then e to the t. The next step is going to be calculating the capital T unit tangent vector. I know that p prime of t is a tangent vector, but capital T of t is going to be my unit tangent vector. So that means I have to divide by the norm of p prime t. And so the norm of p prime t is then going to be the square root of
on the second, so et cosine t minus e sine t.
Thank you. Yeah, that's important. Good catch. So the norm here is going to be the square root of every component squared and then all added together. So if I want to square the first component, that's going to give me e to the 2t sine squared t plus 2 e to the 2t sine t cosine t plus e to the 2t cosine squared t. That's just the first component. If I want to square the second component, that's going to be e to the 2t cosine squared t. And this is a lot of math, so if you find me making a mistake, help me out and point out my mistakes. e to the 2t cosine t sine t plus e to the 2t sine squared t plus e to the 2t for my third component. I think we can probably simplify what's under the square root here. Like this plus 2 e to the 2t sine t cosine t cancels with this minus 2 e to the 2t sine t cosine t. And then in these cases where I have a sine squared plus cosine squared plus cosine squared is just 1. And so this is going to simplify nicely. I mean, not like really nicely, but better than the full version. This is going to be e to the 2t plus e to the 2t plus e to the 2t. So that's 3e to the 2t. Yeah. And so if I take the square root, you know, I can rewrite this again as root 3 and then just e to the t. So this is going to be a gnarly vector. It's going to be root 3 over 3 times the first component, which after I divide by e to the t is just going to be sine t plus cosine t. The second component, after I divide by e to the t, is going to be cosine t minus sine t. The third component, after I divide by e to the t, is just going to be 1. So I have something like this. And that is my capital T unit tangent vector. So the velocity is like the first derivative, which we already found. The acceleration, remember, is like the derivative of the velocity. So that would be like the second derivative of my parametric curve. And so if I'm trying to take the second derivative, that would be like the derivative of this. That's going to be not very fun. I'm going to rewrite p prime of t. So p prime of t was e to the t sine t plus e to the t cosine t. And then it was e to the t cosine t minus e to the t sine t, I think. And then it was e to the t. Yes, cool. Okay, so that's p prime. I just need to take the second derivative, or the derivative of that. So the derivative of that is going to be product rule again. It's going to be and then the product rule for e to the t cosine t is going to be this should be minus. I won't make the same mistake twice. Minus. Okay. So that is the first component. And there's a simplification I can make there. I see it. I'll do that here in a second. The second component is going to be the same thing, except I'm going to switch the signs on this first couple of terms here. So this second component should be negative e to the t sine t minus e to the t cosine t plus e to the t cosine t minus e to the t sine t. And then the third component is still nice little e to the t. So let me try to simplify. The first component simplifies because the e to the t sine t's cancel, and I just get 2 e to the t cosine t. And then the second component, the cosines cancel, and I get minus 2 e to the t sine t. And then the third component is e to the t. Okay, so that's my second derivative. That's my acceleration. Where do we go from here? So to find the principal unit normal vector, you would take capital T prime of t divided by the norm of capital T prime of t. If you want to find the tangential component of acceleration, remember from the formula, this was just my acceleration vector, that one, dotted with the unit tangent vector, which we have also found already. If you want the normal component of acceleration, you can take acceleration dotted with the principal unit normal vector, and then that's how you would find it. From a standpoint of like driving a car, if you're like an F1 engineer and you're trying to design a good race car, you need to know what the normal component of acceleration is so that you know how much traction you need up from your tires, right? Those big race cars have those really super wide tires that are supposed to be really, really sticky. It's so that they can take turns really fast. And even though turning at a high speed is going to create a lot of normal component of acceleration, you know, the tires are designed well enough to keep the car on the road, so you don't have your car flipping every time you try to take a tight turn in an F1 car. So anyways, y'all have a good day.